as soon as a source is connected to an inductor, there exists a potential difference, or there exists an instantaneous voltage which is given by V is equal to Vm sin omega t. V is nothing but Vm sin omega t from equation 1, and E is nothing but minus dl by dt from equation 2, which is equal to 0. The quantity omega L in the expression is analogous to the resistance, and that is called as inductive reactance, which is denoted by XL. Hello everyone, welcome to session 2 of chapter 7 Alternating Current. This is Swati from Department of Physics, Vidhyaashram University College, the Temple of Excellence, Mysuru. The children, in the last session we have learnt about the differences between AC and DC, and we have even gone through about the introductory part of AC parameters, and we have learnt about an important expression when AC source is applied to a pure resistive circuit. In today's session, we are going to understand the other two conditions. What if an AC voltage is applied to a pure inductive circuit? What's the expression of current we get? And we also going to learn about what if an AC source or AC voltage is applied to a pure capacitive circuit. So let us start with expression for instantaneous current when AC source is applied to a pure inductive circuit, which means we are going to derive an expression for instantaneous current when AC voltage is applied to a pure inductor, and we have to draw a phasor diagram for the current which is represented graphically. So for that, we have considered a simple circuit where an AC supply is connected to an inductor. This is the circuit symbol of inductor, which is denoted by L. So in the circuit diagram, L is the inductance of the inductor connected to an AC source. Now, as soon as a source is connected to an inductor, there exists a potential difference, or there exists an instantaneous voltage which is given by V is equal to Vm sin omega t. So what is Vm? It is nothing but the peak value or peak voltage, and omega is nothing but the angular frequency. Since it is an inductor, now the EMF will induce in a circuit, whereas in the previous case we have considered Ohm's law. So now we have to consider the self-inductance, because there is no influence of another coil in the circuit, there is only one inductor. So the self-induced EMF in the circuit or in the inductor is given by E is equal to minus L into di by dt, which is the expression for self-inductance or EMF of a self-inductor. That is my equation 2. Here di by dt is nothing but the rate of change of current. We have learnt about this expression in the previous chapter very clearly. So now I'm applying KVL to the circuit. Since it is a closed loop, we can apply the Kirchhoff voltage law, where we have the term of voltage as well as the EMF. So the Kirchhoff voltage law says that the sum of the potential and the EMF will always be equal to 0. So V plus E is equal to 0. That's my third equation. Now substituting the values of V and E, we get V is nothing but Vm sin omega t from equation 1, and E is nothing but minus dl by dt from equation 2, which is equal to 0. And this now can be equated as Vm sin omega t is equal to plus L into di by dt. When this shift to the other side, it will become plus L into di by dt. So now we need the term current. That's why we are retaining the term di by dt to my LHS and bringing all the terms to the other side. So what do we get? Bringing this term to one side, we will get Vm divided by L sin omega t, which is equal to di by dt, which is nothing but the rate of change of current. By integrating this, we will get the total current. That's why we are retaining the term di by dt to one side. So we get di is equal to Vm divided by L into sin omega t dt. Because multiplying this dt to the other side, we get di is equal to Vm by L into sin omega t dt. To obtain the current or the total current at any instant of time, we have to integrate the above equation. So integral of di is equal to integral of Vm divided by L sin omega t dt. So when you integrate, when you join, when you combine the small amount of currents, we get the total current, that is I, which is equal to Vm divided by L. That's constant because instantaneous voltage and the inductance, they have no changing values, and we have to integrate the function sin omega t dt. So when you integrate sin omega t dt, we get minus cos omega t divided by omega. So substituting that in the above equation, we get I is equal to Vm by L into minus cos omega t by omega plus constant. It can be proved that the value of constant will be equal to 0 over a period of time. So I is equal to Vm divided by omega into L, will get omega L into minus cos omega t. So here we have minus cos theta, which is nothing but sine theta minus 90 degree. So this can be written as sine omega t. In the place of theta I have omega t minus 90, we can write it as pi by 2. This is our equation 4. So here Im is nothing but Vm divided by omega L, and that is the peak value of current. So what is this omega L? The quantity omega L in the expression is analogous to the resistance, and that is called as inductive reactance, which is denoted by XL. So XL is nothing but omega L. So the equation Im is equal to Vm. In the place of omega L, I can replace it by XL. So I get Im is equal to Vm divided by X into L, where X into L is inductive reactance. So this X into L can also be written as 2 pi F into L, because omega is 2 pi into F, where F is the frequency. And what is the SI unit of inductive reactance? Since it is analogous to resistance, the SI unit is ohms. Now let us represent this in phasor diagram. So we have an equation for voltage, that is V is equal to Vm sine omega t. That is my first equation. And my fourth equation is for current, that is I is equal to Im sine omega t minus pi by 2. This is the fourth equation. Now observe both. So here they are not similar, they are not same in phase, but they have a phase difference of pi by 2, which means 90 degree phase difference we can observe in current. So the current is lagging to voltage by an amount of 90 degree. So for that we have to consider a graph of V and I versus omega t. Along x-axis it should be omega t, and along y-axis it should be voltage or current. As usual, we have two signals here. One is for voltage, the other one is for current. You can see here, if they are in phase with each other, then they have to start from same point, like the previous condition what we have studied. This is voltage and this is current. Now you can observe here, they are not starting from the same point, but the current is lagging by 90 degree to voltage. They are out of phase. The phase difference between voltage and current is almost 90 degree. So now projecting this gives us the peak value. The vector of red line, this one represents the peak value of voltage, and here we have the peak of current. They have a phase difference of 90 degree, and this is the peak value of current. So this vector represents the peak value of current, and the angle, the difference between them is 90 degree we can observe. So the projection to vertical axis gives the instantaneous value of voltage, which is represented by expression Vm sin omega t. Similarly, since we have peak for current in this direction, we have to represent the vector in vertical y-axis towards downwards, and it is Im sin omega t minus pi by 2. Since there is a phase difference of 90 degree, we can observe the two vectors in the opposite direction. So what is the conclusion? The current lags the voltage by pi by 2, which means there is a phase difference between the voltage and current. The current is behind the voltage by 90 degree. So let us see the next case now. What if an AC voltage is applied to a pure capacitive circuit? So we will derive an expression for instantaneous current in this case. So let's derive an expression for instantaneous current when an AC source is applied to a pure capacitive circuit, and also we have to represent this in phasor diagrams, which means a graphical representation. So here I have considered an AC source which gives an instantaneous voltage, that is Vm sin omega t, when it is connected to a capacitor. So this is a simple circuit where we have only capacitor and an AC source. So the capacitor C is connected to an AC source. So in the circuit diagram, C is the capacitance of the capacitor and it is connected to a AC source here. Now, as soon as the AC source is connected to a capacitor, there exists a voltage, a potential difference, which can be given by a formula V is equal to Vm sin omega t, where Vm is the peak value of voltage and omega is the angular frequency. So now, the potential difference across the capacitor is given by V is equal to Q divided by C. So we are choosing an expression in such a way that if we have the value of Q, then we can find the expression for current easily. So V is equal to Q by C is my second equation. equation. Let us substitute this in first equation. What is the first equation? V equals Vm sin omega t. So here in the place of V, if I substitute Q by C, we get the equation Q by C is equal to Vm sin omega t. We can multiply C to the RHS and we get the expression Q is equal to Vm into C sin omega t. So Q is nothing but the charge. We know the rate of flow of charges gives us the current. So from that we can write the expression for current I is equal to dq divided by dt. Or we can write d by dt of Q is nothing but Vm C sin omega t. Now, by keeping this, we can arrive at the expression for current when an AC source is applied to a pure capacitive circuit. So, I is equal to d by dt of Vm C sin omega t is what we have. Now, Vm is the voltage and C is the capacitance of a capacitor which do not vary with respect to time, and we have to differentiate only the term sin omega t. So, d by dt of sin omega t gives us omega cos omega t, and hence we get the expression I is equal to Vm into C. They are same, the constant, they are not changing. Differentiating d by dt of sin omega t, we get omega cos omega t. So this is nothing but I is equal to Vm C omega. Cos theta can be represented in terms of sine by the formula cos theta is equal to sine theta plus 90 degree. So we can write cos omega t as sine omega t plus 90, that is pi divided by 2. So I is equal to Im sine omega t plus pi by 2 is our third equation, where Vm C into omega is nothing but term Im, which is nothing but the peak value of current. So we have Im is equal to Vm C into omega, because we have replaced Im in this place, Vm C into omega. So what is Vm divided by M? It can be written as 1 divided by omega C or C omega. So this 1 by omega C or C omega is called as the capacitive reactance, and it is given by a letter called XC, which is analogous to resistance, and the SI unit of this capacitive reactance is also ohms. So XC is equal to 1 by omega C. Omega is nothing but 2 pi f. So we can also write XC as 1 divided by 2 pi f into C. Now we have got two equations, that is V is equal to Vm sin omega t for voltage. That's my first equation. And here from this for current, the third equation, it is nothing but I is equal to Im sin omega t plus pi by 2. This is my third equation. So from this first and third equation, we will come to know there is a phase difference between the voltage and current of about pi by 2, which means the phase angle between the current and the voltage is nothing but 90 degree. The current is ahead of voltage by 90 degree. So let us represent that graphically. So for that we have to consider omega t along x-axis, voltage or current along y-axis. As usual, we have two waveforms here. One is for voltage, the red color waveform what you are observing. The other one is for current. You can see here, they are not in phase. If they are in phase, they have to start from the same reference point. They are out of phase now. There is a phase difference of about 90 degree between the voltage and current. Current is leading the voltage. You can see the peak of voltage is here and the peak of current is here. So current is leading the voltage by 90 degree. So let us extend this to write the vectors which gives us the peak values and instantaneous values. So the vector of V here, the peak of voltage, that is the peak value of voltage V, and here the peak of this green line, that is current. So that is here represented as this vector, that is current. So here you can observe there is a phase difference between current and voltage of about 90 degree, and the projection along y-axis gives the instantaneous value of voltage and current. So instantaneous of voltage is Vm sin omega t, instantaneous value of current is Im sin omega t plus pi by 2. There is a phase difference of about 90 degree between these two. We have to represent this with the phase angle, that is pi by 2. So this is the phasor diagram when the AC voltage or the AC source is connected to a pure capacitive circuit. And the conclusion is current leads the voltage by 90 degree. From the phasor diagram, we can conclude the current is 90 degree ahead of voltage. So in this session, we have learnt the two conditions when an AC source is applied to a pure inductive circuit and pure capacitive circuit. So this is very important for examination also. So in the next session, let us learn some more interesting concepts. Until then, keep learning all of you. See you all in the next session. Thank you.